Hi guys, so in this lecture video, I will be discussing total and net ionic equations. So what are these types of equations right here? And why do we have to use them in addition to the other types of equation that we have been writing all this time already? So first of all, the types of equation that we have been writing previously are referred to as the conventional chemical equation. And this conventional chemical equation right here do not always accurately describe what's happening in the course of a chemical reaction. Yes, believe it or not, they do not correctly describe what is going on in a chemical reaction. And mainly, the solubility of the substances are not correctly being considered in the conventional chemical equation that we have been writing. And so for an example, here is a conventional chemical equation right here. So we have potassium chromate reacting with barium nitrate. And as you can all recognize already, when we mix these two solutions together, and they will be undergoing a double replacement reaction where we will be producing potassium nitrate as one of the products and barium chromate as another product in here. So that is our conventional equation for this reaction right here. So what is not so right about this chemical equation is that the solubility of some of the reactants and the product are not correctly described. For an example, when we write potassium chromate together as an aqueous, that is kind of incorrect a little bit. And the reason why is because the minute that we make a solution out of potassium chromate, the potassium and the chromate actually do not stay together as a compound. So to write them together as a compound, it is not correct. But what is truly happening is when we make a solution out of potassium chromate, what we'll be getting will then be a beaker or a solution that consistent of the potassium and the chromate ion by themselves. Because this substance right here is soluble in water. So when we make a solution out of it, then they be broken up into individual ions. So this is exactly what we have here in this substance. But this ion right here are not together as a compound as being described here in the conventional equation. So that's something wrong about the conventional equation. And similarly with the barium nitrate. So when we write barium nitrate together as an aqueous, then this is also not accurate as well. Because the minute we make a solution out of barium nitrate, then the barium and the nitrate will be broken up into individual ions, in which we have one barium and two of this nitrate ion right here that flowing around. But again, the ions are not together as a compound. So to say and put them together as a compound on the conventional equation, that will be inaccurate. Okay, and now let's move on to the product side. On the product side, we have potassium nitrate. And again, to say that potassium nitrate staying together as a compound is not accurate because this substance right here is soluble in water. So technically speaking, what we'll be having will then be this ion right here that is floating around in this solution. The only thing that is correctly described in this conventional equation right here would then be the barium chromate. This is a solid. And now, truly, this is actually what happened in this reaction. Once this is being produced already, this is a solid, and there we go. We have this solid floating around in here. Now, so it's important that we basically look at the solubility of these substances right here to understand what is going on in the course of this reaction. So when we combine a solution of potassium chromate, which is basically this beaker right here, and with another beaker containing the barium nitrate, then this beaker right here, when we combine these two beakers right here together to perform this chemical reaction, then now we end up with a larger beaker with all of this ion in them. So that basically is what happening on the reactant side. The minute that we begin mixing all of both of this solution together, we will be having one big beaker containing all of this ion. And now here's what happened right here. Because all of this ion right here have charge to them, right? So they be attracted each other. So for example, this nitrate is negative, so it can be attracted to anything that is positive. So basically in this solution, all of this ion will be floating around. And so this nitrate right here may be attracted to this potassium because they have opposite charges. But if the nitrate and the potassium are attracted to each other, they will form a compound, and this compound is soluble in water. So what happens is that it will be broken up into the individual ions again. So basically, nothing productive come out from it, and it get back to where it started out with. And similarly, the nitrate can also bind to the barium because again they have opposite charges. But if bariums were to bind with nitrate, it will form barium nitrate, and barium nitrate is also soluble in water as well. So basically they would be broken up into individual ions again. So nothing productive come out from it. And similarly, when the barium binds to the nitrate down here, same thing happen. However, the only thing that now can create a difference is as follows. If barium were to now bind with the chromate, barium is +2, chromate is -2. So when these two ions are attracted to each other, they form a very strong ionic interaction among them. And now they will be producing something that is insoluble in water. So that's why that the minute they get a chance to interact with each other, they come together as a compound, ionic compound, and become insoluble in water. So thus, they fall out of solution as a precipitate that we observe over here. So that's what happened right there. Now, the potassium and the nitrate would still be floating around in a solution as individual ions. So that is what happened in this reaction right here. And clearly, the conventional chemical equation that we have seen above doesn't really describe all of this detail right here. But all of this detail right here are being described or can be further described in another types of equation that we call the total ionic equation. So the TIE, total ionic equation. So the total ionic equation is the chemical equation that we can rewrite from the conventional chemical equation, in which that now it can accurately describe the solubility of all of the substances in the chemical equation. And here is an example of how the total ionic equation for this previous reaction would be. So here is total ionic equation. So basically right now, on this beaker right here, when we combine these two beakers together, then what happened, it will be having a beaker containing the potassium ion and the chromate ion. And we also have ion from this other beaker, the barium and the nitrate as well. So that basically would be all of the ion that we will find on the reactant side the minute we begin mixing these two solutions together. We have a solution of all of this ion. And now, as I mentioned before already, the ion go and find themselves. And in this case, when the barium interact with the chromate, it now produces something that is insoluble in water, and that's what we would have here on the product side. And the two potassium and the two nitrate ion will still be floating out in solution. They're not together as a compound, right? So thus, but then they remain as separate ions that is soluble in water. So thus, it's important that we keep these ions separately as well, but we do not combine them together. So there you have it. This equation right here is called the total ionic equation. It is the equation that now can describe correctly the solubility of all of the substances in a chemical reaction. Okay. So now, what is the net ionic equation then? So the net ionic equation is abbreviated with NIE. So what is going on with this net ionic equation? It is another type of equation that we can also write, in which that it can truly describe the changes that are happening in a chemical reaction. As a chemical reaction is happening, not all substances may be undergoing chemical change, but only a few of the substances would be undergoing change, but not all of the ions, right? And so therefore, the net ionic equation would tell us, or it will be a chemical equation that we would write to truly describe only the changes that we observe in a chemical reaction. And if we were to be looking at the total ionic equation above, so here it is down here again, you would then see the following. The potassium is present on the reactant side. And now it's also present on the product side as well. So what's going on? That basically means nothing happened to this potassium, right? If it's present before and after that means nothing happened to it. And similarly with the nitrate, we have the 2 nitrate before on the reactant side, and we also find this 2 nitrate on the product side as well. So nothing happened to this nitrate either, but they remain in solution before and remain in solution at the end of the reaction. Nothing happened to them. And so basically we're going to see that the potassium and the nitrate do not undergo any chemical change in this reaction above. And they are present on both sides of the chemical equation. And this ion right here, this potassium and this nitric ion, are then referred to as the spectator ions. The spectator ion are the ion that simply float around in solution to observe the course of the chemical reaction, but they do not really play any role in the chemical chain that we observe in a chemical equation. So again, that are called the spectator ions. So once we have removed the spectator ion already, it would then tell us exactly what is happening in this reaction. So truly, in this reaction right here, what happened is when we have chromate and barium that find each other, they now form something that is insoluble in water, and they fall out as a precipitate. And there we have it on the net ionic equation. By removing the spectator ion because they do not participate in the reaction, what we would then have left would then be the barium plus 2 and the chromate negative 2 that come together to form this insoluble ionic compound right here. Okay, so let me just recap again one more time. There are 3 different types of equations that we have seen. First is the conventional equation. And again, the conventional equation, it does not describe the solubility of all of the substances correctly. Okay, and then moving on to the total ionic equation. This is when we consider the solubility of all of the substances. Okay, and now that we have the net ionic equation, the net ionic equation tells us exactly what are the chemical changes that are happening in a reaction. Okay, so that's the differences between these 3 types of chemical equation. And now, let's go over the guidelines. How do we write all of this equation right here? Just to make sure that we have this down and you are able to write TIE and NIE. So these are the steps right here, how to write total ionic equation and the net ionic equation. So for any double replacement reaction or single replacement reaction, we can write the TIE and the NIE for them. And here are the steps right here. First, we would start with the balanced conventional equation. So please do not forget to balance your chemical equation first. So start with the balanced chemical equation. And we also need to include the physical state of each of the substances. Whether something is solid, a liquid, a gas, or an aqueous, please specify all of that. All of that are very important when writing total and net ionic equation. And after we have the balanced conventional equation already, this is then what we will then do next. We will be looking at each of the reactants and the product, and for all soluble ionic compound. So ionic compound that we have identified as an aqueous because they're soluble in water, and strong acid. That is when we would separate these substances right here into ions. Because soluble ionic compound and strong acid are substances that the minute that we make a solution out of them, they actually breaks up into individual ions. So therefore, to truly describe what is happening with them, we will then separate them into ions. Okay, and make sure we also include the stoichiometric coefficient for them. For example, if I were to have 2 sodium chloride, 2 in the front of the sodium chloride, a coefficient is 2, then now have 2 sodium plus and 2 chloride negative. So that's what this means right here, include their coefficient. Now, never separate solid or molecular compound or liquid, gas, or weak acid into ions because they do not exist as ions when we make solution out of them. And because they do not exist as ion, therefore we should not break them into ion. Got it? So only break soluble ionic compound and strong acid into ions. Okay. Now, so this is where you need to be able to use the solubility guideline to figure out whether an ionic compound is soluble in water or not. Okay. And as for the strong acid, this is something that we have to kind of remember. And here in this class right here, there are 7 acids that we would consider to be the strong acid. And these are the 7 strong acids right here. Plus, all binary acid except for HF. So this basically includes HCl, HBr, HI. All of these are strong acid. So there you go, we have 3 of them. And now there are 4 of the oxy acid that are also considered to be strong acid as well. And they are the nitric acid, the sulfuric acid, the perchloric acid, and the chloric acid. So this is the chloric and this is the perchloric acid. So these are the 4 strong oxy acid right here. And combined together, these are the 7 strong acid. So only for these 7 strong acid that we would break them up into individual ions. All of the acid other than this 7 strong acid right here are then considered to be a weak acid. Okay, so that's how we can identify the soluble ionic compound and the strong acid. And so after we have done this already, we will be able to then write the TIE. And once we have the TIE already, we can then identify and remove the spectator ion from the TIE. And so the spectator ions are the ion that we see on the reactant and the product side. In order for them to consider as the spectator ions, everything about them have to be the same. For an example, if we talk about an iron's ion, iron plus 2 and iron plus 3 are not the same thing. Okay, so if we find iron plus 2 on the reactant side and iron plus 3 on the product side, they are not the spectator ions. Okay, because in order for them to be considered as spectator ions, everything about them, including the charge, has to be the same. If they're not the same, then they're not spectator ions. Okay, so once we have our TIE already, now identify and remove the spectator ions, and then write the equation for what is remaining, and that would then give us our NIE. Good. And now, so here is one of the practical tip right here regarding TIE and NIE. So the one of the question is, for a double replacement reaction, can we write the NIE without writing the TIE? A lot of time we are interested in the NIE because we are interested in the chemical changes that are happening in a reaction, right? So therefore, a lot of time we focus on this NIE. And right now with this 3 guidelines right here, we start out with the conventional equation, and then we write the TIE, and then we identify the spectator ion to remove the spectator ion, and finally arrive at the NIE. But the question now is that, do I have to write the NIE in order, do I have to write the TIE in order to write the NIE? And the answer is yes. You don't have to write the TIE to be able to write the NIE. And here is the trick right here. So if basically on exam and quizzes, that we simply ask you to write the NIE for this equation, then don't, and we're not asking for the TIE, then don't spend your time writing the TIE because that will not help you answer your question quickly, right? So here is how you'll be able to write the NIE without the TIE. And again, this is something that would be applicable in a double replacement reaction only. So here's what you would be looking at. You would then be looking for the driving forces in that double replacement reaction. What is the driving force of this reaction right here? If the driving forces of this reaction is the formation of a solid, then whatever ions that make up this solid right here, that is then the part that become important on your NIE. Good. And if your driving force is a liquid, for example, water, then now what kind of ions that make up that liquid? Then those ions right there would then be left behind on the NIE. Got it? And similarly, if we have a gas at the driving force, what kind of ions make up this gas right here? Then those would be left on the NIE. Does that make sense? So hopefully that will be a good trick right there to help us write the NIE quickly without the TIE. So let's try a few of the problem right here, writing TIE and NIE. So here is an example. Nickel nitrates and sodium carbonate solution are combined, forming solid nickel 2 carbonate precipitate and a solution of sodium nitrate. So here in this case right here, we are giving you the products as an example, but on quiz and exam, then please be expected to be able to predict this product right here yourself. Okay, so now let's follow the step. Based on what we've been told in here, first, write the balanced conventional chemical equation. So here in this case, we have the conventional equation. So first we have nickel 2 nitrate, and the chemical form nickel 2 nitrate is Ni, NO3, 2. And this is soluble in water, right? So therefore this is an aqueous. And the other solution is sodium carbonate. Sodium carbonate is Na2, CO3, and this is soluble in water again. So therefore this is an aqueous. And now on the product side, we are forming nickel 2 carbonate precipitate. So the formula of nickel 2 carbonate is NiCO3. And now this is a solid. It is insoluble in water. And the other product, sodium nitrate, which is NaNO3. And this is soluble in water, so therefore it is an aqueous. So there we go. That is our conventional equation. And now make sure this is balanced. And this equation right now is not balanced. To balance this, we need to put 2 in front of the sodium nitrate. And now we have a balanced conventional equation. And now the second step, write in our TIE. So here we're going to learn to write all TIE and NIE. Right now, I can be writing the NIE without even writing the TIE. But again, we want to practice writing TIE and NIE all together. Okay, so here in this case right here, to write the TIE, first we inspect the first compound. And right now, to see if this is soluble in water. And we have done the work already when we apply the solubility and determine that this is an aqueous right here. So this is an ionic compound and it is an aqueous, meaning it's soluble in water. So therefore, we're going to break this up into ions. Okay, and when we break this up into ions, it will be producing a nickel that is +2. Now, it is very important that we include the charges on these ions. This nickel right here has a charge of +2, and now it is an aqueous. Okay, and now as for the other ion, then now we have 2 of this nitrate, right? So make sure we also include that out as a coefficient as well. So for every one of this formula, there are 2 of the nitrate. So now I'm taking this subscript and I'm bringing it out to the front as a coefficient. So 2 of the nitrate. Each of the nitrate is -1. That is charge. And now it is an aqueous. So that's how we break nickel 2 nitrate into ions. And now similarly, let's do the same thing with the other compound, sodium carbonate. So should we break this up into ions? And the answer is yes, because this is a soluble ionic compound. And this will then be broken up into 2 sodium. Each sodium is +1. And now this is an aqueous. And we will then have 1 of the carbonate. And the charge of the carbonate is -2. And this is an aqueous as well. So there you go. That's what we will have on the reactant side. And now moving on to the product side. Should we break this nickel 2 carbonate into ion? And the answer will be no. Why? Because this is insoluble in water. It is a solid. So do not break a solid into ions. So therefore, we're going to keep this nickel carbonate the same thing. And it is a solid. And as for the last substance, we now have sodium nitrate. Should we break up sodium nitrate into ions? And the answer is yes, because this is soluble in water. And now, make sure we distribute this 2 right here to each of these ions. So what this means is that we have 2 of the sodium and 2 of the nitrate. So 2 Na, and each of the sodium is +1, and now it is an aqueous, and 2 of the nitrate. Each is -1, and it is an aqueous. So there we have it. This equation right here is then our TIE. And now let's write the NIE. to write the NAE, then we need to identify and remove the spectator ions, right? Here in this case right here, if I didn't have to write the TIE, I will be able to write this Na as follows. I will then see that this is my driving force right here for this reaction, right? The formation of this solid. And this solid right here consists of nickel and carbonate. So therefore on my NAE, I have nickel plus 2 and carbonate negative 2 that are coming together to form nickel carbonate. So that will be left behind on my NIE right there if I were to skip writing the TIE. But here in this case, we have our TIE already. So let's now identify and remove the spectator ions. So here in this case, when we inspect this, I see that I have 2 nitrate right here and 2 nitrate on the product side. So this present on a reactant and the product side, so that will be a spectator ions. And the same thing with the sodium, the 2 sodium on the reactant and 2 sodium on the products. That will be the spectator ion as well. So when we remove this, what we would then left? Again, so the nickel and the carbonate and this are together, so they are not the same thing, right? So therefore, that would not be our spectator ions. So what we would then left behind would be nickel plus 2, aqueous, combining with carbonate, negative 2, aqueous, producing nickel carbonate, solid. So that will be our NIE right there. And again, this is the driving force. So the ion that make up this driving force, that what consists, that what being left behind on the NIE. And so just to go over a few more points right here, the important, make sure we include the charges. Okay, so please do not forget the charge. If you don't get the charge correct, you'll be losing point on quizzes and exam. And another thing to also consider, you do not forget to distribute the coefficient if there is a coefficient. So we need to distribute the subscript to both the subscript and the coefficient. Okay. Let's now try a few more practice problems. So please give this a try first before you look at the answer key together. But now let's try some of this problem. So the mixing of sodium chloride with silver nitrate solution. What would be the conventional, the TIE, and the NIE for this reaction right here? So I'm gonna let go of this one together. So first, sodium chloride is NaCl, and this is soluble in water, so it will be an aqueous. Reacting with silver nitrate is Ag, NO3, and this is soluble in water again, so therefore it is an aqueous. So when we mix these two solutions together, if there is a reaction, it will be a double replacement reaction, right? So the sodium, which is the cation, would now be binding with the nitrate. This is +1, this is -1, this is +1, this is -1. So the sodium would now be forming compound with nitrate. So we will be having NaNO3. And when we apply the solubility guideline to this, we can see this is soluble in water, so it is an aqueous. And now the silver will be forming compound with the chloride. That will be the other products, AgCl. And now AgCl is insoluble in water, so it is a solid. Okay, so this would be our conventional equation right here, and right now it is balanced. So let's now write the TIE. So here in this case right here, in writing the TIE, we should be breaking sodium chloride into ions, into Na plus and the Cl -1. And we should also be breaking silver nitrate into ions as well, because it is soluble in water, into silver +1 aqueous and the nitrate -1 aqueous. So that's what we will have on the reactant side. On the product side, should we break sodium nitrate into ion? And the answer is yes, because it is an aqueous. An ionic compound that is an aqueous means it's soluble in water. So it breaks up into sodium plus aqueous and nitrate aqueous. And again, do not forget to include their charges. And lastly, with the silver chloride, should we break this up into ions? And the answer is no, because it is a solid. It is insoluble in water. So make sure we keep this together. So that would then be our TIE. And now as for our NIE, then when we identify and remove the spectator ion, we see that sodium is present before and after. So that is spectator ions. And the nitrate is also another spectator ions. So when we have removed those already, what we now will have left would then be the chloride and the silver ions that are combining together to form silver chloride solid. Okay, so that will be our NIE. And here in this case right here, we kind of knew this already, because we know that here in this reaction right here, the reason why that there is a reaction here in this case is because the silver chloride, that is our driving force. So whatever ions that make up this substance right here would then be left behind on our NIE. Okay. And now let's try another example. So let's go over another reaction in which that it is not a precipitation reaction. Okay, so here in this case, let's try a reaction number 3. So solution of hydrochloric acid and sodium hydroxide reacting with each other. What will be the TIE and the NIE for this reaction right here? So let's now first get started with the conventional equation. So hydrochloric acid would then be HCl, and this is an aqueous reacting with sodium hydroxide, NaOH, aqueous. So that's what we will have right here. And again, this is a double replacement reaction. So we figure out we want to predict the product. Make sure we state the charges, right? So here the hydrogen is the +1, the chloride is -1. Here the sodium is the +1, and the hydroxide is -1. So if anything gonna happen, the hydrogen would now be forming compound with the hydroxide, and that would then be producing water. And we all know water is a liquid. And now the sodium would now be forming compound with the chloride, because sodium is +1 and chloride is -1. When they form the product, it will be NaCl. And now when we apply the solubility guideline, this is soluble in water, so it is an aqueous. And by checking to make sure this is balanced, it is correctly balanced already. And now, so let's now write the TIE for this. So first, should we break HCl into ions? And the answer is yes. Why? Because it is a strong acid. Okay, so it is strong acid, so we should break HCl into ions. And this would then be broken up into the hydrogen ion. Because strong acid, by definition, are basically substances that would dissociate or ionize it into ions. And one of the ions that they are becoming would be the hydrogen ion. So it becomes the hydrogen ion and the chloride ions. So those would be the ions that will be produced from HCl. And now moving on to sodium hydroxide. Should we break sodium hydroxide into ions? And the answer is yes, because this is a soluble ionic compound. So we have sodium ion, aqueous, and the hydroxide ion, they are aqueous. So let me, okay, there we have it. And now moving on to the product side. Should we break water into ion? And the answer would be no, because this is a molecular compound. Molecular compound do not exist as ion, right? So this is a liquid. Do not break a liquid into ion. So keep water the same thing. H2O. And how about sodium chloride? Should we break this into ion? And the answer would be yes. Into sodium plus aqueous, and the chloride aqueous. So there we have it. This would then be the total ionic equation for this reaction. Oops, so where did my page go? And now let's write the NIE. And in the NIE again, make sure we remove the spectator ions. So the chloride is one of the spectator ion because it's present in both the reactant and the product side. And the sodium as well. And again, guys, please remember this, that the charges has to be the same thing in order for them to be considered as the spectator ions. And I think that will be it. So what we will have left will be hydrogen aqueous combining with hydroxide aqueous and producing water liquid. So that will be left behind on our NAE. So here in this reaction right here, the hydrogen ion and the hydroxide ion combine together to form water. So this is the only chemical chain that is happening in the course of this reaction. Okay, and again, we see that in this reaction right here, we kind of knew that this would be the NAE already, because when we look at the conventional equation, we would then observe that the formation of water or this molecular compound is our driving force, right? And this driving force substance right here is consistent of hydrogen and hydroxide. So this is why that this will be left behind on the NIE. Okay. And now let's try another example. This example number 5 right here. What would be the TIE and the NAE for this reaction right here? So a piece of zinc solid is added to a solution of lead-2 nitrate. So let's go over this one. So zinc is a solid. Is added to a solution of lead-2 nitrate, which is PbNO3 2. And this is soluble in water. Again, all ionic compound consistent of nitrate is soluble in water. So here in this case right here, what kind of reaction is this? And we will then see that this will be a single replacement reaction, right? So we have to use the activity series to determine whether there will be a reaction or not. In this case right here, if anything going to happen, zinc will be replacing lead. And we will then see on the activity series, zinc is actually more reactive than lead. So zinc will be able to replace lead. Okay? So therefore, the product that we'll be producing is as follows. Zinc would now be forming an ionic compound with nitrate. And that would then form zinc nitrate. And when we apply the solubility guideline, we'll then see that this is an aqueous. And now lead is being replaced, so now become an element. And all metal in the elemental form, they are solid. And their charge equal to 0. So there we have it. This would then be the conventional equation for this reaction. And it seems that it is balanced already. Let's now write the TIE and the Na for this reaction. So here in this case right here, zinc, nothing is happening to it, right? So it remains the way it is. How about now moving on to lead-2 nitrate? Should we break this up into ions? And the answer is yes. So this becomes Pb, and the charge on this Pb right here is +2. And we would then have 2 of the nitrate. Each is -1, and this is an aqueous. So again, please do not forget to distribute this 2 out in the front. And moving on to the product side. Should we break this zinc nitrate into ions? And the answer would be yes, because it is soluble in water. And this would then breaks up into zinc +2. So that's the charge on this zinc right here. And 2 of the nitrate. And as for this lead right here, it is solid, so we could write it the way it is. So that is our TIE. And now, let's now write our NIE. To write the NIE, we need to identify and remove the spectator ions. So are there any spectator ions here in this reaction? And the answer is yes. So first we have the nitrate. We have 1 nitrate, 2 nitrate on the reactant side, and 2 nitrate on the product side. So that is a spectator ion. How about the zinc? Will the zinc be a spectator ions? So look at its charges. Look at the charges. The zinc on the reactant side is neutral. the zinc on the product side is an aqueous and a choice plus 2. So are they the same thing? And the answer is no, they are not the same thing. So therefore, the zinc are not the spectator ions. Okay, how about the lead? The lead here on the reactant side is plus 2 and it is aqueous, versus on the product side is neutral and it is a solid. So they're not the same thing, right? So again, that is not our spectator ion either. So there you go. We only have one spectator ion here in this reaction, and that is the nitrate. So let's now write the equation for what remaining. So we will have zinc solid combined with lead 2 plus aqueous, producing zinc plus 2 aqueous, and this lead neutral right here, that is a solid. So there we have it. That's the NIE of this reaction. Now, because this reaction right here is referred to as a redox reaction, but redox reaction is not something that we'll be covering here in this lecture. Okay, so therefore I'm not going to get into much detail about this. This equation right here can also be referred to as the redox equation of this reaction.